Imagine the air around you, just humming with invisible radio waves. The stuff that connects our phones or laptops.
Yeah.
It's everywhere.
But what if these waves could do, like, way more than just carry our calls and cat videos? What if they could become a way to actually see in the dark? Or maybe give us a clearer picture of that invisible wireless world that powers our lives?
That's a cool thought.
Well, today on the deep dive, we're going to tune right into that idea.
That's right. And for you, the learner, we've taken a really good look at some fascinating new research. It's a master's thesis, actually, exploring how to use these radio waves, RF signals, to, well, map out our surroundings.
Great.
So think of this as getting the inside scoop on some really innovative thinking, but without having to wade through all the dense, technical stuff yourself.
Exactly. Our goal today is to pull out the most interesting bits, the useful insights from this work. And it basically looks at two related challenges, doesn't it?
First, how can we map the structure inside buildings? And second, how do we create detailed maps of the radio signal environment itself?
Yeah, they're connected.
It's like trying to understand both the bones of a building and also how energy, like wireless signals, flows through it, all using the same unseen tool, radio waves.
And what's interesting here is that the thesis proposes two different, though, like you said, connected ways to do this.
Okay.
The first one they call UBMap. That's all about creating real-time maps of building interiors.
Real-time, okay.
And the second, SpecNRF, that focuses on efficiently figuring out these radio environment maps, or REMs, which are, well, super important for making sure our wireless networks actually work well.
Got it. So UBMap for inside buildings, SpecNRF for the radio signals themselves. Let's tackle that first puzzle then. Seeing inside buildings with UBMap.
Sounds good.
Now, we're not talking like Superman's X-ray vision here.
Not quite.
But the basic idea is, maybe surprisingly, a bit similar. These researchers developed a system for mapping indoors in real time using a technique called radiotomographic imaging, RTI.
And the reason they looked into this is, well, it's really compelling. Current ways of mapping indoors, like SLAM, that's simultaneous localization and mapping.
Right, where robots try to build a map and figure out where they are at the same time.
Exactly. Those often run into problems. They don't work so well when they can't directly see things, like what's on the other side of a wall.
Line of sight issues.
Precisely. Plus, they can need a lot of computer power. Now imagine firefighters going into a burning building.
Right.
They might not have accurate blueprints or they're outdated. But knowing the layout, maybe even what the walls are made of, that could be absolutely critical for a successful rescue. This radio wave seeing technique could potentially drastically change how they navigate, give them real-time intelligence that they just don't have now.
That's a powerful motivation. Okay, so RTI, it tries to see through walls using radio signals. How does that work, basically?
Well, the idea is that different materials block or absorb radio waves differently.
Like how a thick wall blocks sound more than, say, a thin curtain.
Exactly like that. So by measuring how much the radio signal weakens or attenuates between different points, you can start to build up a picture, an image of what's in between.
An attenuation image, they call it.
That's the term. However, the traditional ways of doing RTI, well, they often require setting up special equipment beforehand.
Okay, infrastructure.
Right, using sensors that need very careful calibration, and like we mentioned with SLAM, often using a lot of processing power, which, can make them difficult to use in lots of real-world situations.
Right, not ideal for emergencies. But this is where their approach, UBMap, gets really clever, doesn't it?
Yes, I think so. UBMap is designed to be, well, lightweight, easy to use, doesn't need any special gear already installed.
So what does it use?
It actually uses the Wi-Fi chips that are already in our smartphones, or maybe wearable devices like smartwatches.
Oh, wow. Just everyday tech.
Pretty much. It uses them to do the sensing from different locations in a distributed way. They even use a smart protocol, find time measurement, FTM. It's kind of like indoor GPS using Wi-Fi signals to estimate how far apart the different sensing devices are.
Okay, so they're using phones or wearables, figuring out the distances between them. How do they turn that into a map of where the devices are?
Yeah, that's a key step. What's ingenious about UBMap is how it estimates these relative positions. Imagine you just have a bunch of distances between different points.
Like dots on a page, but you only know how far apart they are.
Exactly. And you're trying to arrange those dots on a map based only on those distances. That's essentially what a technique they use called classical multidimensional scaling, or CMDS, helps UBMap do. It creates a basic layout of the devices.
Okay, CMDS for device layout. But if you're just walking around with these devices, in your pocket or on your wrist, you're not going to know your exact location constantly. That seems like a big hurdle.
It absolutely is. That's a major challenge, location uncertainty. Ubique Map tackles this with a really neat system they developed called Grid Find.
Grid find, what does that do?
It intelligently figures out the best level of detail, the best resolution for the map grid. You don't want to zoom in too much if your location data isn't super precise, right? Because you might just end up with a blurry, inaccurate picture.
Makes sense.
But you also don't want to be so zoomed out that you miss important details, like smaller walls or obstacles. GridFind tries to find that sweet spot dynamically.
Dynamically adapting the map detail based on location fuzziness. Clever.
And GridFind also uses another smart trick based on something called the Akaike Information Criterion, or AIC. It helps them distinguish between measurements where the signal likely traveled in a straight line between devices.
Line of sight, laudum des.
Right. And those where it was probably blocked or bounced off things, non-line of sight, NLS, within each grid cell. This helps them make better sense of the signal attenuation data they're getting.
Okay, so they know where the devices roughly are, they know how fuzzy that location is, and they have a better idea if the signal path was clear or blocked. How do they build the actual map from there?
They go even further. Ubique Map uses what they call a robust tomographic reconstruction method. Instead of just assuming they know exactly where the radio signals went between the uncertain device locations.
Which they don't.
Which they don't. They make an educated guess, a kind of probabilistic estimate. They call it a stochastic approximation of the signal path. This accounts for that location uncertainty we talked about. And the result: it actually leads to clearer, higher quality maps compared to older techniques, like standard Tikhonov regularization.
So embracing the uncertainty actually makes the map better.
In a way, yes. It makes the reconstruction more robust to that noise.
Okay, so now they have this attenuation image, this picture of how radio signals weaken across the space, built using this robust method. How do they turn that into a nice, clean map of walls and obstacles?
Right, the final step. UbiCap uses some image processing techniques, things like Laplacian of Gaussian filtering and morphological skeletonization. Fancy terms, but basically they help sharpen the edges in the attenuation image and highlight the thin lines that correspond to the building's structure, like walls.
Cleaning it up to look like a floor plan.
Essentially, yes, an obstacle map.
And what did they find when they actually tested this out? Did it work in the real world?
They did. They used UbiMap in a real apartment, about 800 square feet, and also a larger building foyer, around 3,000 square feet. And the system created maps that were significantly better. They quantified it as 30 to 40% higher map quality compared to other state-of-the-art RTI systems using similar kinds of mobile Wi-Fi devices.
Wow, 30–40% better. That's a pretty notable improvement.
It really is. And what's particularly impressive, I think, is that Ubique Map can map enclosed spaces and areas where you can't see directly from one point to another.
The places where SLAM struggles.
Exactly. What's a big advantage over those SLAM-based methods? Plus, the accuracy of the map doesn't rely quite as much on the specific path the mobile devices take, which is another issue with SLAM sometimes.
Less sensitive to how you walk around.
Right. And get this, they even showed that it could reconstruct maps using only measurements taken from outside a building.
Wait, really? Mapping the inside from the outside just with Wi-Fi.
That's what their experiment suggested. It's pretty amazing.
That really makes you think about the possibilities. You mentioned mapping structure, but could it see other things?
Well, they saw hints of that. Beyond just mapping walls, they even observed patterns in the data that suggested UbiMap could potentially detect things like furniture, maybe even human presence, inside closed rooms.
Oh.
And while their initial attempts to actually identify different materials based on how much they attenuated the signal were more qualitative, just observations, really.
Not hard numbers yet.
Not yet. But the potential for future, more quantitative analysis is definitely there. Imagine, like you said earlier, first responders being able to tell if a wall is maybe wood or concrete, just using a device sensing these radio waves. That would be huge.
It's incredible. And they did this with just Wi-Fi ranging.
Yeah, and it's also fascinating that UbiMap achieved this level of accuracy using regular Wi-Fi signals, which, as we noted, aren't always super precise for measuring distances compared to other technologies like ultra-wideband, UWB.
Which is more specialized.
Right. So it shows how robust their method is, how well it works, even with less than perfect location information coming from standard Wi-Fi.
Did they try scaling it up, like bigger buildings?
They ran computer simulations on larger floor plans, and these tests confirmed that the grid find system, the one that picks the map detail level, really helps in choosing the right resolution, especially when there's more noise in the location estimates.
Okay, so grid find scales well.
Seems so. And another interesting finding from the simulations was that the mobile devices, the agents carrying the sensors, only needed to explore about 40% of the total area to create very accurate maps of the whole space.
Only 40% coverage needed. That's efficient.
Yeah, it suggests you don't need to meticulously cover every square inch.
Makes sense.
And finally, they looked at the trade-offs, how the number of devices you use, how fast they're moving, and how long it takes to actually generate the map are all connected. Understanding these practical aspects is essential for figuring out how best to use the system in different real-world scenarios.
Right, the practicalities. Okay, so that's Ubique Map, a really powerful tool for seeing the unseen inside buildings. Let's switch gears now to the second challenge, creating radio environment maps, or REMs, using this other system, SpecNRF. First off, why are these REMs so important?
Okay, REMs. They're essentially maps that show how radio signals travel and, critically, how strong they are in a particular area.
Like a signal strength map.
Exactly. And these maps are incredibly useful, increasingly vital, actually, for planning and managing wireless networks, especially with the growth of advanced tech like 5G and, whatever comes next.
Right.
By understanding where the signal is strong and where it's weak, network operators can figure out the best places to put cell towers, access points, other equipment to provide good, reliable coverage.
Avoiding dead spots.
Precisely. Imagine city planners using these kinds of dynamic maps to proactively identify and fix wireless dead zones, ensuring seamless connectivity for everyone. That's kind of a cornerstone of modern smart cities, isn't it?
Absolutely. That makes total sense. So how have these REMs been created typically? Sounds like it would take a lot of work.
It does. Traditionally, yeah, it's a lot of effort. The main method involves manually collecting data, often called war driving.
Driving around with sensors.
Right, or
Yeah.
walking around with special equipment to measure radio signals everywhere. This data is then used, often with interpolation techniques, to create the map. But as you guessed, this takes a lot of time, costs a lot of money.
And I bet it gets outdated fast.
That's the crucial part. You have to do it all over again pretty much every time something in the network changes, like if a cell tower is moved or repositioned. The thesis actually points out that even moving a transmitter by just, say, 12 meters, that's less than 40 feet, can significantly change the radio environment. They found a median change of about 8 dB, which is substantial. Your old map becomes inaccurate fast.
Wow. Okay, so that sounds really inefficient, especially with how quickly wireless networks are evolving. How does SpecNRF offer a better approach?
Well, this is where a really interesting technology called neural radiance fields, or NERF, comes into play.
NERV. Wait, isn't that the thing used for creating, like, amazing 3D models of scenes from just a bunch of 2D pictures?
That's the one. SpecNRF cleverly adapts this technique. Instead of images, it uses radio signal measurements to estimate REMs in a much more efficient way. The key is that it needs only a minimal amount of new measurements, even when the network setup, like a transmitter location, changes.
Okay, that is an interesting connection. Using NERF for radio waves instead of light, how does it work? Are they feeding signal strengths into a NERF-like model?
In essence, yes. SpecNRF has two main parts. First, it uses a smart approach to collecting the initial data, what they call optimized war driving.
Optimized word driving, okay.
So instead of just randomly gathering measurements or driving every single street, it looks at satellite images. It uses an AI model, actually the Segment Anything model, or SAM, to identify important features in the environment that will likely affect how radio waves travel things like buildings, primarily.
Focusing on the obstacles.
Right. Then it uses a route planning algorithm, like a traveling salesman problem solver, to figure out the most efficient path to collect data primarily in and around these key areas.
That's smart. It's like saying, let's not waste time measuring everywhere. Let's focus on the places that really shape the radio signal.
Exactly. Very efficient. The second part is the NeurF-based REM estimation itself. SpecNRF trains a type of artificial neural network, a multi-layer perceptron, or MLP,
Okay, a neural network.
to learn the relationship between where the radio transmitter is located, which direction it might be pointing, and how strong the signal is received at many different locations throughout the area.
So it's learning the rules of radio propagation in that specific environment.
Precisely, based on that focused set of measurements from the optimized war driving. And importantly, this training process can happen relatively quickly, even on a fairly standard computer or device. They emphasize doing it locally.
Locally, okay. Does it model the 3D space?
It does. SpecNerf uses a 3D grid system, voxels, to model the space, and it implicitly learns how signal strength decreases, attenuates, as it passes through different learned material properties within that grid. They also use a data augmentation technique, basically interpolating between their collected measurements to create more training examples, which helps improve the accuracy of the final ARM.
Makes sense. More data helps the network learn better.
Mhm.
So how well did SpecNerf actually perform? How did it stack up against those traditional methods?
The results they presented were quite encouraging. In their simulations, SpecNerf achieved accuracy that was as good as, or in some cases even better than, traditional interpolation methods like inverse distance weighting or radial basis functions.
Okay, comparable or better accuracy?
Yes, and importantly, its predictions showed lower variance, meaning they were more consistent and reliable. This was especially true when they simulated changing the transmitter's location. SpecNerf adapted much better with fewer new measurements.
Ah, so it handles changes more gracefully.
Exactly. And that optimized data collection path we talked about, that also proved to be significantly more effective than just taking measurements along random trajectories. You got better results with less data.
So efficiency wins again. It really sounds like a potentially significant step towards making REMs much more practical, more dynamic, more adaptable to the constantly shifting wireless landscape.
It definitely seems like it. Now, it's important to note that while SpecNerf showed strong promise in these simulations,
Right, simulations aren't the real world yet.
exactly, the researchers point out that actually deploying and testing it in large-scale, real-world networks is the logical next step. Currently, they mentioned the initial training of the NERF model takes around 20 minutes.
20 minutes. Still maybe a bit long for real-time updates.
Perhaps, but they believe this time could be reduced significantly with further software optimization, maybe using techniques like instant NGP, which has sped up visual nerve training dramatically, so there's potential for faster updates.
Okay, good to know. So let's try and bring this all together. This research, looking at both UBMAP and SpecNerf, really shows us some amazing new ways to harness the power of those invisible radio waves all around us.
Absolutely. I mean, UBMap offers this vision, this potential future, where we can create detailed maps of the insides of buildings without needing any pre-installed infrastructure. That could be truly transformative for fields like emergency response, construction, maybe even robotics.
Yeah, definitely.
And SpecNerf provides a much more efficient, scalable, and adaptable way to understand and predict wireless coverage, which, as we've said, is increasingly vital in our super-connected world.
The thesis also hinted at some exciting future directions, didn't it? Things they might explore next.
It did. They mentioned ideas like maybe integrating visual nerve systems with these RF systems, sort of combining sight with this radio sense.
Oh.
Also, automating the process of figuring out the best places to put transmitters using these learned REMs and scaling these techniques up to handle even larger, more complex, and maybe even dynamic environments where things are changing all the time.
Wow.
It really feels like we're just scratching the surface of what might be possible here.
It does.
And for you, the learner, listening in, consider this provocative thought. Imagine a future where those first responders we talked about have real-time, detailed maps of hazardous environments right there on a handheld device.
Instant situational awareness.
Right. Or maybe a future where your phone, your car, all your devices always have a strong, reliable wireless connection because the network itself is constantly learning and optimizing based on these kinds of detailed, up-to-date radio maps, all thanks to the very radio waves that are constantly surrounding us unseen. What other surprising uses might we find for this kind of RF sensing technology down the road?
Some truly fascinating possibilities to think about there.
Yeah.
Thank you for joining us on this deep dive into the world of RF-based sensing and mapping. We hope this has given you, our learner, a clear and insightful look into this really cutting-edge research.
Yeah, we tried to tailor this exploration to your interest in gaining that knowledge efficiently but thoroughly, and we hope it hit the mark for you. Please feel free to share any feedback you have or perhaps any further questions that popped up.
And be sure to join us for future deep dives. We'll be exploring other intriguing topics, all based on the materials that you share with us. Until next time, keep exploring the world around you.